Everyone, welcome to Advent of Code Day 17, Clumsy Crucible. In this video, I'll be going over my solution to the problem in Python after going over the problem description and sort of how I approached it. Let's get right into it. So for this problem, we're pushing a crucible full of lava through a city and trying to pick a route through the city that minimizes the heat loss on the crucible. So our inputs look like this, and essentially each single digit is a city block, and we can think of the number meaning corresponding to how much heat we would lose passing through that block. So what we want to do is find a path from the top left to the bottom right, such for the crucible, such that the crucible minimizes, such that we minimize the heat loss. Heat loss being defined such that each tile we touch from the start, we incur that heat loss. So if we went like 2, started up here, went down, we would incur a heat loss of 3, went right, we would incur a heat loss of 2, went right again, heat loss of 1, went down, heat loss of 5, etc. To make this a little bit more difficult, there are a couple ways that, couple restrictions on how the crucible can move. So essentially, the crucible can only go in a straight line for 3 blocks at a time. What that means is that if we start in this top left, we go right, right, right. We've gone right 3 times. Now we must take a 90-degree turn, meaning in this, say we started here, started this 3 and went right, 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 ended up on this 6. Our next move must be either to the 5 above or the 6 below. And we can only, in this example, we can only move along the 4 cardinal directions, no diagonal moves. So what this means is that our search is going to have to account for the fact that we can't take any paths that are longer than 3 steps in any one direction. For this, what we can do is essentially construct a graph using this input and then perform or run Dijkstra's algorithm, which finds the shortest path from this node to this node. But there are a couple of intricacies in how we do that. To explain more, let's just go into the code. All right, so here is my solution. Let's go into my solution for part 1. So what I do is first go through the input and get essentially creating this hash map heap, which contains the heat of each XY position. Sometimes I like to use row and column, but I think X and Y is maybe a little clearer. I'm thinking about X going along each row, X increases, and then Y going down each column, Y increases. So 0, 0 is up here, and then the maximum values of X and Y are down in this bottom corner. Then I create this hash map called min heat, where this will store the minimum heat or heat loss incurred to get to each node. So, for example, to get from x of 0, y of 1, which would be here, this 3 here, the minimum heat loss we could incur is just by going straight down from the start, so that would be 3. And basically, we're filling out this dictionary, this hash map, as we perform Dijkstra's algorithm, and then we can pop off the value at the bottom right corner to get our final answer. So what's notable here is that I am defining this new class point, or this new type point. If we go to the definition, point is a tuple of not 2 integers, as you might think, which would correspond to x and y coordinates, but of 5, where the first 2 elements are the x and y position. The third and fourth elements are used to describe the direction of the crucible at each point. Since we have this added complexity that we we can't go more than 4 steps at each, um, or can't go like more than 3 steps in a row in each direction. We have to keep track at each node of not at each node in the graph that we're searching over of not only the position, but the directions and the steps remaining. So the third, fourth, and then the fifth element is the steps remaining. So for example, um, the third and fourth would be like the velocity in the x direction and the velocity in the y direction. For example, if we start at this top left corner, go down to the 3, now our point would be defined by x equals 0, y equals 1, dx equals 0 because we're not moving in the x direction, dy equals 1 because the current direction we're increasing y by 1 each time, and then steps remaining would be 1 because we started here 1, or I would be 2, I guess. It would be 2 because we started here, we've moved down once, so we've taken 1 step and we have 2 remaining before we must turn. So that is sort of the main part, or the main, I don't know, the most conceptually complex part of this problem, is that we can't just search over a graph that contains these points. Yeah, our graph has to contain information about the direction and steps remaining as well. From there, it's sort of just implementation details. So we define the min heap dictionary. Now we just perform Dijkstra's algorithm. Um, so we create a heap using the heap queue Python library. We start out, our initial position is not just, since we're keeping track of direction too, we start out at x0, y0, but could be facing to the right or to the left, which is why we're adding 2 of these values to the heap. And we're actually not adding 2 values, but the adjacent points to these 2 starting values. Yeah, so that's that. Then we continue to iterate until the heap is empty, in which case we'll have completed Dijkstra's algorithm. Definitely recommend looking up Dijkstra's algorithm and how it works if you're not super familiar. Because yeah, I'm not going to completely explain it here, but that is essential to understanding this problem. What we do then is, since the heap, elements of the heap are tuples, where the first index is the heat at which we got to that point. So we start out with a heat of 0, but this will build up as we traverse. And then the second element is the point, which remember is actually, again, a tuple of 5 integers. So we first validate that the point is within the bounds of the search. Then we check if we're in the bottom right square. Since in Dijkstra's algorithm, the first time you reach a point will be, we know that we're never going to get there any faster. So in that case, we can just return the heat at that point, which is the heat that it took to get to that point, plus the heat at that point. Yeah, otherwise, we can update this min heat dictionary as we go. And then making sure that if we are not decreasing the min heat at each point, then we can just continue our search. We don't care about exploring that branch further. Whoops. Yeah, going back to where we were, finally, we use this get adjacent function to return the adjacent points from the point we're currently at, and add all those onto the heap. So this function essentially takes in a point, remembering that a point is described by 5 integers, and returns the adjacent points. I'm not going to describe exactly how this logic works. It is a little bit tricky to think about, But essentially, in this branch, we return the neighbors if we have 0 steps remaining and need to make a right angle. Here, we handle the case if we have steps remaining, in which case the adjacent points include going forward, or we could also turn before we're out of steps. So yeah, that is relatively simple if you understand all those concepts. Implementing this was a real challenge. I had literally almost 100 lines of code trying to just debug, printing out like the paths, and I just couldn't figure out while I wasn't working. And it just had to do with some of these constants here, setting the steps remaining properly and all of that. So yeah, this was a challenging problem, but that's part one. Let's run it on this example to make sure we get the correct solution. Get 102, and that's indeed correct for part one. Now let's move on to part two. Part two, we're dealing with ultra crucibles, which function slightly differently in that they must follow at least four, they must go at least 4 blocks in the same direction before turning, but no more than 10. And so essentially, we have like a path that looks like this through our example, where we can see that we're going in longer stretches, but they're of minimum length 4 and maximum length 10, of course. So let's see how that's implemented. Essentially, our problem is, almost exactly the same. The differences are that we use a different function to get the adjacent points because we run out of steps. I sort of flipped around. Instead of using steps remaining, I do steps taken, just because I thought that was a little bit more intuitive for the second part. So if we've taken 10 steps, we must turn. Then, if we've taken greater than 4 steps, we're allowed to turn. We can still go straight. Yeah, the only other point that should be addressed is that in this case, we actually need to run the search until it's exhausted instead of breaking out once we hit the final point, because we actually can sometimes get to the final point with a lower heat later. So basically, this code is there to do that. Running this on the example, we see we get 94, which is indeed correct. So yeah, that does it for day 17. This was quite a challenging problem, but didn't require too advanced algorithms knowledge. Dijkstra's algorithm, I did have to look it up exactly how it's implemented, but pretty simple, just use the heap. So yeah, that's it for day 17. Any questions or comments, leave it below. And yeah, thanks for watching, and I'll see you in the next one.